Hi, everybody. We are going to be talking about section 12.1 today. So this lecture will be underneath dynamics lecture number 5. You'll notice that we have 2 days where I will talk about section 12.1. That's because it's very foundational, and there's a lot of techniques that we'll learn here that will benefit us for the rest of our time together in dynamics and also in other engineering, science, and mechanics classes. So for that reason, we really want to make sure that we understand this material well. So as in the past, when I have recorded this lecture, which will be very shortly, instead of having the assignment icon, you will have the link icon, meaning that the lecture is available to you via vodcast and via YouTube. All right, so beginning with Chapter 12. Chapter 12, I wanted to change this a little bit. Chapter 12 we're talking about Newton's second law of motion, and specifically we are talking about the kinetics of particles. Now in Chapter 11 we talked about the idea of kinematics, meaning the description of motion. In this chapter we are talking about kinetics, which also focuses on the cause. And as you may know, Newton's second law tells us that force in a vector sense is equal to mass times acceleration. So the cause of linear accelerations is forces in general. So therefore, when we talk about kinematics, we're really talking about forces. And my PowerPoint decided to freeze up on me. There we go. All right, so we're going to be talking a little bit about these ideas today, and we're going to get really quickly into the idea of linear momentum and how that relates to forces and acceleration as well. We're also going to be talking about systems of units, because the metric system and the U.S. customary system deal with force and mass differently from each other. But as I've hinted in class, and also I've if you haven't, you may have heard it elsewhere, that force and mass, weight and mass are not the same thing. So the relationship between them is determined not only by Newton's second law, but also by what system of equations or system of units that we're using. Okay, so to begin, Newton's first and third laws are sufficient for the study of bodies at rest. But in order for us to study accelerating bodies, we have to talk about Newton's second law. So basically, Newton's second law, F equals mass times acceleration. We know that acceleration is equal to dv dt, or the change in velocity with respect to time. So anytime that we change velocity, we have to talk about Newton's second law. And the other thing about velocity is to remember that velocity is a vector, so we're not just talking about magnitudes. In other words, we're not just talking about speeding up or slowing down, we're also talking about changing the direction of our velocity. So Newton's second law, stated in English, is that a particle will have an acceleration proportional to the magnitude of the resultant force acting on it and in the direction of the resulting force. What that means is gravity, for example, acts downward. So if the force of gravity acts downward, it is never going to result in a motion to the right or to the left. It's always going to be downward. And if you push on something horizontally, the motion will be horizontal. It will not veer off into some odd direction. Now, that also, of course, is dependent on the system of coordinates that we use and so forth. But basically, what we're saying is that the force and mass force and acceleration are proportional, both in terms of magnitude and direction. Turns out that the scalar proportionality for that is the mass of the object. All right, the resultant of the forces acting on a particle is equal to the rate of change of linear momentum of the particle. And this may be something that's not that familiar to you, but basically, if you think about acceleration, acceleration is dv dt, and momentum is mass times velocity. And I'll show you the equations for this in just a moment. But what that really means is that if we are talking about dv, mdv, if linear momentum is mv, then the rate of change of linear momentum is mdv. So Newton's second law then says if the resultant force acting on a particle is not zero, the particle will have an acceleration proportional to the magnitude of the resultant and in the direction of the resultant. So when we take a look at some of these ideas, we say that acceleration must be evaluated with respect to a Newtonian frame of reference, one that itself is not accelerating or rotating. The math just gets a lot more complicated at that point. So the big deal equation that we start working with is Newton's second law expressed as a mathematical equation that the vector force is equal to the scalar mass times the vector acceleration. And since force and acceleration are both vectors, mass is a scalar, the direction of the force and the direction of the acceleration will be identical. So then the last part of this just says that if a force acting on a particle is zero, the particle will not accelerate. In other words, it will remain stationary or continue on a straight line at constant velocity. Now, in everyday life here on Earth, if you take a ball, for example, and you roll it on the floor, it will not continue rolling in the same direction in a straight line at a constant velocity forever because it's being acted upon by friction. However, if you throw something up in the air, it's not, for a different reason, it's not going to continue going up in the air forever. It's being acted on by gravity. So when you see something that doesn't behave in that manner, that it's not continuing in a straight line at a constant velocity, if it moves with no net force, that means that there is a net force. So you have to analyze it to think about what that means. I'd like to frame this in a little bit better if I could, but it may not be possible. All right. So basically then we have, like we talked about before, we have force is equal to mass times acceleration, which itself is dv dt. So if we pull m inside of the derivative, we can say that it's d mv dt. It's not going to change the value because mass is a scalar. And we refer to the linear momentum, or m vector v, as vector L, L for linear momentum. So what this is saying then is that the summation of forces acting on a particle is indeed equal to mass times acceleration, but it is also equal to the rate of change of linear momentum with respect to time. So linear momentum is a conserved quantity. If the resultant force on a particle is zero, the linear momentum on the particle remains constant in both magnitude and direction. That's very useful to us when we are solving problems. So when we start talking about systems of units, here's kind of the fun part. We have four primary dimensions: force, mass, length, and time. And all of them, length, time, are independent. Force and mass are directly related to each other. In the SI system, they use units of mass more frequently. A unit of mass in the SI system is a kilogram. But in the US customary system, it's more common for us to use units of force. And the unit of force we use is a pound. So you're probably familiar with the ideas of kilograms and pounds. But it's important to note that they do not represent the same primary dimension. They're related to each other through gravity or through weight, but they are not the same. So once again, here we go to metric system or international system of units. What we do is we start with a kilogram, we accelerate it at unity, which is just at 1 meter per second squared, and we develop a unit of force or a unit of weight of newtons. So 1 kilogram meter per second squared is the same physical quantity as a newton. Now, since Earth's standard gravity is about 9.81 newtons, if we plug that in here, we can see that a 1 kilogram object weigh means the exact same thing as subjected to a gravitational field, 9.81 9.81 newtons, because the acceleration is 9.81 newtons, and 1 times 9.81 is 9.81. All right, in the U.S. customary system, it's a little bit different. When we see this term, which is not too common, this LBM stands for pound of mass. The acceleration of gravity, the identical quantity to 9.81 meters per second squared. If you convert meters per second squared, you find that that quantity is 32.2 feet per second squared. And this results in a unit that is the standard unit of mass, which we don't use very often, but the standard unit of mass in the U.S. customary system is referred to as a slug. So in other words, 1 slug times 1 foot per second squared is equal to a weight or a force of 1 pound. All right, so just sort of to recap, summation of forces equal mass times acceleration. And we need to remember that everything needs to be broken down into vector components. In this case, if we're using rectilinear, ijk. So we can say that the force in the x direction is equal to mass times the acceleration in the x direction, similar in the y and the z. We also remember that acceleration is equal to the rate of change of position with respect to time, differentiate twice. So it's the second derivative of position with respect to time, so which we can also represent as x double dot in the x direction, y double dot in the y direction, and z double dot in the z direction, just indicating that we're talking about the second derivative of that position in that particular direction with respect to time. Now we use tangential and normal components very often, and we developed an expression last time for the acceleration in the normal direction, which is v squared over rho, where rho is that radius of curvature, and acceleration in the tangential direction, or along the path, which once again, this is all the rate of change of speed, dv dt. This is all the rate of change of direction. All right, now another way to think about this is if summation of forces equal mass times acceleration. Since mass is a scalar and acceleration is a vector, we can think of mass times acceleration as a vector itself, and it is sometimes referred to as the inertial or the inertia vector. And what that means is that is the natural tendency that has to be overcome in order to stop or move that particle. So in other words, to make it do something different, you have to be different than the inertia vector. So in other words, this is just another way of writing the same equation. If the summation of forces minus the inertia vector is equal to 0, that's exactly the same thing as saying the summation of forces is equal to the inertia vector, or is equal to mass times acceleration. So you notice here we have 3 instead of just being an equal sign. This is 3. That means it's defined as being the inertia vector. All right, so if you include the inertia vector, that means that the equivalent force is going to be equal to 0 if the particle is in dynamic equilibrium. Previously, if we don't include the inertia vector, if the summation of forces is equal to 0, that means that we're in static equilibrium. The particle is sitting still. This means that it's moving in dynamic equilibrium. So there's an acceleration involved in that, or could be, if we, depending on how we choose to use it. All right, or depending on the situation of the particle. Methods developed for particles in static equilibrium may be applied as long as we take into account that inertia vector. So that's pretty cool. And the inertia vector are often called inertial forces, as they measure, just like I stated before, the resistance of the particle to offer change in motion, whether that change in motion is direction or speed. So in other words, the larger the inertia vector, or the larger the inertial forces, the more applied force needs to be in order to move, or the more different it needs to be in order to move the object. And inertial forces may be conceptually useful, but are not like the contact and gravitational forces found in statics. It's not an externally applied force. All right, so here's a sample problem, and I'm going to run through this with you. And after we finish this problem, we're going to be done for the day, but there are a few things that I want you to see on this problem. First of all, I want you to be careful about drawing the picture. The picture is called a free body diagram. Free body diagram conceptually takes the object that you're interested in. In this case, I suspect it's going to be the 200-pound weight, and then looks at everything that acts on it. So the 200-pound block is acted upon by forces. There is this force P, and if you think about it, there's also a weight, and it tells me that the coefficient of friction is 0.25, so there's also a frictional force. So I draw the weight, I draw the friction as a force, and I draw the weight as a force, and I put P as a force before I start doing any of the equation work. All right, now you may remember, if you've had physics before, that there is a normal force, the frictional force mu k times the normal force N is equal to the force of friction, generally speaking. Now mu k stands for kinetic, meaning that it's moving. The force of static friction generally is higher than the force of kinetic friction, meaning that it's harder to get an object moving than it is to keep it, or I should say accelerating, than it is to keep it accelerating. But moving is okay for this application. So in other words, the normal force is perpendicular between the surface of contact between the block and the table in this case. But if we're at an angle, if we're on an incline, the force would still be perpendicular to the surface of contact, so it will have an angular relationship to the plane of contact. But here it's vertical and horizontal. So we draw this, this is a free body diagram. Once again, we draw the block, we draw the normal force, we draw the frictional force, we draw the weight, and we draw P. Then we set it equal to the inertia vector. All right, so we know that in the x direction, that the summation of forces, the components of forces in the x direction will equal mass times the inertia vector. Mass, once again, can't stress it enough, is a scalar, so it's the entire mass. Now, if we were not able to solve everything with the x direction, we could also do a y direction, which would say summation of forces in the y direction is equal to the mass times the acceleration, or the weight of this object. All right, so we resolve, we take P. P makes a 30-degree angle with the horizontal, so the component P in the x direction is P times the cosine of 30. The normal force is purely vertical, so it has no component in the x direction, as is the weight. But we do have the force of friction, which is mu k, or the coefficient of kinetic friction, times the normal force. Okay, so then we can set those two things equal to P cosine 30 minus the inertial force is equal to, or excuse me, the frictional force is equal to the mass times the acceleration. Now, the mass of this object, if we go back, we know that my weight is 200 pounds. I need to change that weight into a mass. And the way I do that is I divide by the acceleration of gravity. So in other words, the mass of this object is 6.21 pound second squared per feet, which is exactly the same thing as saying it is 6.21 slugs. It's often better, or it's often easier, more expedient to leave it in base units like this, because then you can see that everything will cancel out. So in other words, seconds squared here cancels seconds squared here, feet cancels feet, and we're left with pounds. And pounds is a good unit for force. So we know that P times the cosine of 30 minus 0.25 N, normal force, is equal to 62.1 pounds of force. Now, the deal is here, though, I have two unknowns in one equation, so I need a second equation, and almost always at this level of study, that will be equal to the other direction force. So we had the summation force is x, now we have the summation force is y. Normal force is vertical, weight is vertical, P has a component acting downward, at a magnitude of P times the sine of 30, but force is purely horizontal, excuse me, friction is purely horizontal, so there's no component in the y direction. So now I have this equation, and what you can see is that this has P and N, two unknowns, this has P and N, same two unknowns, so I can solve those two equations simultaneously to find out the magnitude of both N and P. Okay, the way that it's done here, which is fine. I'll try and get that rid of that. Okay, here we have, no, this went too far, sorry. There we are. So we have, we've solved for N with the summation forces Y equation. And then we plug that in here for N, because then we just have one equation, one unknown, and we can solve for P. Right? We could also solve for N if we wanted to, but we now know that P is equal to 15 pounds. All right, ladies and gentlemen, that is it for today. What I'd like to do is to have you work a couple of problems with these ideas, and then we'll continue with section 12.1 on Wednesday. So please let me know if you have any questions, and I'll see you next week.